Hello everyone, my name is Hayden Hunley, and I was lucky enough to be chosen to be a part of UAH's 2020 RCEU program. My proposal that I was working on this year was to harness satellite observations and deep learning to identify irrigated fields in the state of Alabama. In this project, I was working under the guidance of Dr. Hu, Dr. Zhang, and Dr. Handyside. So irrigation actually plays a vitally important role in our society through the distribution of water to our farms, our houses, our landscapes, entertainment areas, and even more. So to design something like this has a huge impact, increasing the profitability and efficiency of each of those previous things that I just mentioned. Being able to manage how we move our water throughout the state allows us to not only save money, but to also save water by optimally moving the limited resources of it that we have around. The goal of the design of this project was to create a deep learning neural network to be able to read in NASA satellite indexes and output a map of where irrigated lands are. That map would then be used to move water about the state to where it's needed most. A common way to accomplish this without machine learning today is to just manually go through the satellite images and handpick out the center pivot irrigation systems as seen in the picture under design. This takes a lot of time and manpower and can be heavily improved upon using computers. On those images, land that's irrigated actually shows a higher enhanced vegetation index during normal and drought conditions, which means we can just use the change in that value over many years of data to find what land is irrigated and what land isn't. So to begin, I actually researched a few different deep learning approaches, but decided on using a binary tree decision classifier, one that's perfectly simple enough to capture the data and output a binary answer. It's either a 0 for not irrigated or a 1 for irrigated. And I began by splitting all the data that I had into 3 different chunks of categories to be able to error check it. I had a 60%, a 20%, and a 20% split. 60% of the data was used to train the model and the trees. 20% of the data was to find the best tree of those trained models. And the last 20% was used on the best tree that it found to see how the system would work on new inputted data. To train the network, I used the data's Guinea impurity. With each training epoch, I altered the maximum tree depth, starting at 1 and finishing at 25, to find the highest accuracy tree for the data set. If you look at the plot, the training set trains a new decision tree at the max depth of whatever it might be. It outputs that tree accuracy in blue, and then outputs that tree when it's run on the next 20%, the validation set, and outputs its accuracy in orange. As you can see, the higher the max depth goes, the further the split of the accuracies between the training and the validation sets. This shows that the more the depth of the tree, the more the tree incorrectly assigns irrigated and not irrigated values to the data, which makes sense as the decision tree has overfitted the tree onto the original data and doesn't know how to fit onto any new data. The program then runs the best tree onto the untouched set, the test set, showing what the trained tree might do to completely new data. This project was actually able to achieve accuracies of around 85 to 89% on average, with outliers ranging up to 94% actually. The precision score, the recall score, and the F1 scores all lie within 0.87 plus or minus 0.01. With statistics like these, it's hard to say that this project wasn't a majorly successful one. This is a great first step, proving that there is still so much more that can be done. It has such a real-world applicable value to not only the state of Alabama or to any other state, but to the nation as a whole. Thank you guys for your time, and thank you UAH and to all my acknowledgements for this amazing opportunity that was granted to me.